Okay, I hope you're real relaxed right now. I brought in that soothing music because we're going to talk about friction. And friction, it causes that internal dissonance and stress, friction. So, just relax, kind of shrug your shoulders and take a deep breath. And this won't be so caustic to your sensibilities after all. So, here we go. 4 basic categories of friction, and these are better demonstrated to you. So remember to ask me to demonstrate these, especially in case you're confused on any of them. So we have static friction, which corresponds to surface, 2 objects on a surface. Say that this line here is a surface of a table, and we put a block on here. And maybe we tilt the surface up, or we put a little bit of force on one side of the block, but it just stays there. No relative motion. If it wasn't for friction, there would be a little motion, but because of friction, it holds it in place. Then kinetic. Well, if static is surface to surface with no relative motion, kinetic is surface to surface with relative motion. So it's moving. Grab a block, slide it on the surface, you have kinetic friction. Rolling friction? Well, intermolecular bonding, pulling apart as object rolls along surface. Now, if I ask you if this is big or little, you'd be correct if you said little. Take a tire and roll it down the road. Does it come to rest quickly? No, because this little effect here is much more subtle and less effective. Doesn't affect it as much as 2 surfaces rubbing together. This isn't rubbing together. It's just being in close proximity and the small forces involved between the bonds of atoms and molecules. So it's a small value. We know that, all right? A train on a railroad tracks, very low friction, hard steel to hard steel, for instance. Not sliding, but rolling. And then we have fluid friction. Resistance encountered from a viscous medium, like air, water, oil. If you drop a stone in water, it goes through the water, but it's encountering the resistance of the fluid, and therefore slows down or reduces the acceleration, limits the velocity. Drop a piece of paper through the air, you see the same thing. So those are the 4 categories that we're concerned about. Now, kinetic friction. What does it depend on? Well, I could do some experiments, and again, you can ask me to do this. And we discover that kinetic friction depends on something, and it's the normal force. Okay? And it might be instructive to understand why the answer isn't gravity or something else. I can explain that, but for now I'll just give it to you. The normal force, the force of contact between the surfaces. So that probably makes sense. It also depends on the surface material. If you press an ice skate into ice and slide it along, there's very low friction. If you take that same ice skate and put it and slide it against a rubber mat, that surface material has much greater friction, and so there's more of it. Now, it's also independent of some things. We can demonstrate that it's independent of the surface area and the relative speed. Those 2 things don't affect how much friction there is. Given that it is dependent on these things, you could come up with a formula. If it's dependent on the normal force, you could probably guess that if you double the normal force, the friction doubles. You'd be right. So friction depends on normal force in a direct way, but also the surface material. And that could vary because there's an unlimited number of different kind of surfaces. So here's the formula. Kinetic friction is equal to mu k normal. Now, it's proportional to, if I wrote the proportionality symbol, the normal force. You double this, this doubles. The proportionality constant in this equality, see the equality, this coefficient of friction is a characteristic property of, yes, you guessed it, the surface material. So the type of material determines the coefficient of friction, which is the mu. The sub k just means kinetic, moving. let's move on and finish this. The static friction depends on the same things as the kinetic friction. However, the object is not moving. The static friction always acts parallel to the surface, but it's only true when the applied force cannot break the intermolecular bonding. There's no motion involved here, okay? As long as that's the case, that static friction is in effect. So we can write the same kind of equation. Now it's Fs for static. It's mu s normal. When you double the normal force, the amount of static friction available, whether you're using it all or not, is another story. The static friction available doubles as well. And what determines the proportion between them is this. So mu, the coefficient of static friction, that's what that stands for, mu s. It turns out that this is a little bit different than this, because once you break the static object loose, you push on it until it breaks through this static friction, then it immediately becomes kinetic friction. This is a little tiny bit smaller, at least, than this one. And it's really important that it is, because it would be a very strange world we would live in indeed if this was smaller than this. Because as soon as you broke it loose, it would increase and bring it to rest. Once it started moving, it'd come to rest because this is bigger. And then, but then when it's resting, it's smaller, so it would break loose again. It would just be a bunch of fit and starts. That would kind of be insane. Actually, you could argue that you would start pushing on it, and as soon as it starts to move, it would stop. And so really, you'd never get it going. Anyway, it's not the universe we live in. And this is a brief summary of the definition of friction, both kinetic and static.